Good evening, everyone, and welcome to Careers in Technology Summer Series 2024, Session 2. Tonight's speaker is Lou Gullo, and to introduce him, I'm going to hand this over to Rajesh.
Thanks, Michael. I've presented Lou's bio on the screen. I've known Lou since I think I was a teenager. I got one of his when he was at Honeywell, right, Lou? You were at Honeywell, right? Long
Yes,
time
I think so. Yeah, back in the 90s.
Yeah, back in the 90s. Lou's a wonderful mentor and an awesome person to work with. He's mainly focused in the area of reliability prognostics and security fault management. He's worked in the military, the space, telecom, and commercial electronic industries. He's got a couple of patents, and he's also the Reliability Society person from a standards perspective, and he's the author of 3 books. He's recently retired from Norman Grumman.
Oh, Northrop Grumman. Yeah, Northrop Grumman.
Northrop Grumman. And since I have known him, he is somebody who one can go to anything related to reliability and testability. Lou, all yours.
Thank you, Rajesh. So it's a pleasure to be here with you and talk to you about reliability engineering and reliability technology. I was hoping to get a show of hands of how many folks here are thinking about a career in reliability engineering, because I'd really like to target this for those folks that have an interest in and have heard about reliability engineering, maybe went to a conference, read some papers, had taken classes. So show of hands, how many folks are interested in reliability engineering? I see Rocco. I know Rocco was, I met him at the ICPHM, so thanks for being here, Rocco. Who else?
Lou, just so you know, your video is currently off.
Okay. Can you see me now?
Yep.
So how many hands? I saw Christian's there. Hey, Christian, thanks for joining us as well. Met him also at the ICPHM, and he's involved with the Arizona Tucson chapter. And anyone else? Okay, so those 2 folks I already know. So obviously, Rocco and Christian, you guys can reach out to me at any time. I've already responded to email since we met at ICPHM, and if there's something here that you wanted me to deep dive in, we can have either an email transfer, correspondence back and forth, or I'm okay to talk to you one-on-one on any of the questions that you have. So for the purposes of getting through the material, I was thinking maybe I could breeze through everything in 30 minutes if I'm not going to do a deep dive in any of these slides. I've got about 23 slides, so I wasn't going to spend a lot of time talking about the details unless there was somebody that was really interested in learning more. And like I say, if it's Christian or Rocco, feel free to send me an email and I'll follow up with you offline from this. But if there's somebody here, if you could hold off your questions to the end, and then I will address, what slide particular you had a question on. Does that sound fair? Okay, so let me share my screen. I did a practice on this before, so hopefully it's going to cooperate again. Can everyone see my screen?
Yes, we do, Lou.
Okay, so I'm coming to you from the Reliability Society. I'm the Standards Committee Chair, as Rajesh told you, and I'm also involved with the Transportation Electrification Council, It's a new council that just got stood up this year, and they made me, appointed me as their vice president of standards. So I've been doing a lot of work in standards. Since I joined IEEE in 2004, I quickly became the standards chair in 2006 because of all my background helping on developing many of the standards. And I'll talk about some of those standards here. So here's a overview of what topics I'm going to cover. I'm going to go through just quickly in one slide what reliability engineering is all about. So I'll introduce that concept as a discipline for engineering, and then I'll talk about reliability technology and also quickly just touch on that. And then I'll come back to it later on when I talk about design for reliability, and then I'll talk about reliability standards that I'm involved in, either sustaining them or developing new standards. So reliability engineering is an engineering discipline and profession that is involving all stages of a system or product lifecycle. I didn't say this here, but I was thinking later as I prepared this slide to let people know that there are several schools that have been very well known in developing courses in reliability engineering, either bachelor's degrees, master's, or even doctoral and then postdoctoral work. University of Maryland has been very well known in this area. They have at least at one point had two PhD programs, one in systems reliability and another one in mechanical engineering for reliability, like physics of failure modeling. And then University of Arizona was very prolific for a long time, had many books written by Dr. Casey Siaglu. And since he's retired, which is about 10 years now, they've kind of lost interest in keeping that curriculum going, even though there's been several teachers, like associate professors, that came in and taught a few courses on the bachelor side. But they haven't built it back up. And then every now and then I'll see schools like Vanderbilt, Georgia Tech was big for a while, Arkansas will also do courses. So there's a way to study at university level reliability engineering and reliability technology as well. So reliability engineering is critical to many of the industries that exist today. And it's critical because of the need to know that something works consistently over time. And from the time you open the box till the time that that item is out of life or out of service or end of life or needs to be destroyed because it's no longer able to function and the companies that made it don't care about repairing it. And there isn't an easy way, let's say, to fix it yourself. So for systems that need to last for a long time, let's say 20 or 30 years, or systems that are really critical and they don't have to last that long, but when they work, they need to work perfectly. Reliability engineering is a critical discipline. And a lot of that is done through requirements. We specify requirements and analyze those requirements and verify them, test them, demonstrate that products work correctly. And then reliability professionals assess the probability of mission success, and that's a calculated term. So I'm talking about reliability as a probability, could be for mission success, or 1 minus that reliability probability is the probability of failure. So whether you're looking at probability of failure or probability of mission success, those are usually parameters that are specified on contracts. And customers will say what their expectations are for meeting a reliability number over a certain period of time. So reliability engineering is an engineering process and a discipline and a profession. So next is to explain reliability as a technology. So technology, I like to say that there was a commercial back in the day when I was going through school, I think it was 3M, that used to say, we don't make the products that you use, we make the products that you use better. So that's what reliability is reliability engineers don't design the products, but reliability engineers get their hands on the products and then make a recommendation to the design authorities on how to improve that product to be able to last longer and to have a cheaper life cycle cost. So if there's something that is a very costly item to repair, The maintenance is takes a long time, and the parts to replace it are very expensive. Then reliability engineering will recommend that a part be replaced or a process be developed to make the part replaceable faster, or automate the process, or do things like redundancies. So you can have fail safes, you can have fault tolerance, you can have resilient systems, systems that recover um, and heal themselves. That's getting more into resilience, but reliability plays a part in that. So there's an overlap between, let's say, safety discipline, system safety, um, cybersecurity, all the various assurances or sureties that exist in engineering. And design features are put in place for designs to be assessing, whether it's through prognostics or diagnostics capability, health monitoring, to predict failures. That's more of the prognostics, taking the statistics and then predicting what the probabilities are of failure in the future, and then preventing system failure. So you can have multiple failures occur, but the system is still able to accomplish its functions and its mission. So even though maintenance should be performed, it's not critical because the system is still able to perform through it. So here's an overview of the reliability standards, and the Reliability Standards Committee. I'll talk about that in some detail, talk about the history of the reliability standards, how it started in the 90s when the first IEEE standard 1332 was created. I'll talk about the portfolio of the different standards that the Reliability Society manages, either sustains it or develops, and then the latest standards in development. So here's the introduction for the Reliability Society Standards Committee. It's a group in IEEE developing sustaining standards for reliability engineering professionals, develops open consensus-based reliability engineering and related engineering standards, follows the IEEE Standards Association development process. It's a standards board, and the standards board has two committees. One's called the NESCOM, the New Standards Committee, and then the RevCom, which is the review committee. And NESCOM is the part of the IEEE Standards Board that approves a project starting to develop a new standard and give the working group a sanction to go ahead and develop that standard with the intent of publishing it, usually in 3 to 5 years. And then also the RevCom is the other part of the standards board that is involved in approving that draft after the working group has finished drafting it and creating it, and then doing the balloting and making sure that there's a approval within the IEEE community for that standard to be released, or there are comments or problems with that standard that need to be addressed before it can be released. So the Reliability Society Standards Committee, RSSC, has a portfolio of 6 standards, and I show them in that white area. So there's 1332, which is the first standard. That's a reliability program standard. There's 1413, which is the standard framework for reliability predictions, and that's strictly for hardware. 1413.1 is a guidebook to help you select the right approach for doing a prediction based on the 1413 requirements. 1624 is an organizational reliability capability process that relies on 1332. So if you have a program plan, you want to develop reliability processes and have a program to go do that, 1624 is a way to assess the capabilities of an organization to develop that process or that program, or to be able to write an effective program plan. 1633 is a software reliability prediction standard, and that covers predictions that would not be covered in 1413. And then lastly is 1856, which is the PHM, we call it, Prognostics and Health Management. It's also known as CBM Plus, which is Condition-Based Maintenance Plus Prognostics. So that standard is also a normative standard with requirements on how to develop a prognostic system or a PHM system. And then the last point I want to make over here is these are the standards that are statused and currently being updated. So 1413, 1413.1, 1624, and 1633 are currently active right now with a working group working to update that draft, the latest standard, to make it a new draft and then get it approved. Also, one other note I want to say here is that we have 3 different types of documents we call standards in IEEE SA. One of them is a standard, so it's a standard that is a standard, which means it has normative requirements. It has shall statements. There's also recommended practices, which is what 1633 is, a recommended practice, so it's not a normative standard. And then we also have guidelines or guidebooks, which is what is 1413.1. It's a guide. So it doesn't have normative requirements either. So it's more informative to guide a user on how to select the best methods that would meet their needs. Okay, here's a hierarchy of how the standards kind of fit in. 1332 was the first to be developed, and then 1413 was the next, and then these standards all are underneath what we consider the program standard for reliability. And then there's 1413.1 that follows under 1413. And then the standards in development, we have these 4 standards that have either completed development recently or almost near the end, or one of them is fairly new. So I'll just go through. 3106 is a standard for telecommunications system reliability. It develops metrics for telecommunication companies to be able to assess their services that they provide in the telecom community. That one has recently been approved and is planned to be published in this year, 2024. 7009 is fail-safe design of autonomous and semi-autonomous systems. That also recently completed its process, and it was approved to be released to the public in on July 5th this year. 2818 is another standard that has recently gone through the Standards Board approval process. It had to go through recirculation ballot. So when it goes through balloting the first time, if there are problems, lots of comments and problems to be fixed, and the standard is changed, then it goes through a recirculation. And in the case of 2818, it's going through its second recirculation, so it's third ballot. And it's recently been completed the ballot this month. And so that's planning for the Standards Board review and hopefully approval in September. And then last is 1856.1, which is a companion to 1856. So this will be a recommended practice for PHM systems. And that one has been working group has been working on that draft for about 1.5 years now. So I wanted to talk about the history of reliability standards, so you know how far back we've been working reliability standards. The Reliability Society is one of the earliest societies in the IEEE. If I don't remember how many societies there are, but we call those organizational units. So between societies and councils, I think we're near 50. And our society is number 7. So it was the 7th organization to be stood up within IEEE. So in 1992, this is when the Army Material Systems Acquisition Activity, called AMSA, out of Aberdeen, Maryland, and working with the Kelsey Center from University of Maryland, had discussed the possibility of canceling a military standard, military standard 785, which is the reliability program standard that was used for many years. During acquisition reform in the mid-90s, that standard was canceled. And so 1992 is when they talked about the possibility of that standard being canceled and what they would do to replace it. So they decided that if 785 was replaced, that they would develop an IEEE standard that could be used in lieu of the military standard. And the idea was that it was a standard that anybody in the electronics industry, not just a military organization or a defense contractor, would use, but anybody in electronics industry would use it. So in 1998, this first standard was created and published by the IEEE SA. It was sponsored by the Reliability Society and became 1332. The standard was developed under the leadership of the working group chair, Professor Mike Peck from the University of Maryland. He's also the director of the Kelsey Center at the University of Maryland. And if you're interested in further details about this history, I wrote about a 4-page article in the Reliability magazine, which just got released earlier this year. So in the second edition, the article is available there that you can try to get through the IEEE Reliability Society website. So the scope of 1332 is to encourage suppliers and customers to develop reliability requirements, cooperatively integrate with reliability engineering processes into a comprehensive reliability program to satisfy those reliability requirements. So it's really cooperation between suppliers of products or systems and customers that are the end users or the acquisition of those systems that then hands off to a end user. Building a relationship that takes requirements from the customer and then translates them into a supplier's program plan and then tries to achieve an approval between supplier and customer so that the roadmap for developing reliable systems or products is understood and agreed to and will hopefully be adhered to and verified. So these requirements are usually written through contractual documents or obligatory relationships between customers and suppliers working together through the reliability program. The purpose is normative reference, standard with specific requirements designated as shall statements. 1332 standard guides suppliers and customers in planning a program that suits their design philosophy, the system product concepts, the resources at their disposal, which means like having tools or processes or assets that support a reliability program, whether it's testing or analysis, simulations, designing and modeling, so that all these engineering activities add value in terms of improving the reliability of a product or system compared to what the reliability would be if you were just rolling a dice and hoping for the best. Here we demonstrate it, try to prove it, predict it, verify it. So objectives, the objectives are pretty simple. Overall objective is to provide systems and products that satisfy reliability requirements that are agreed to between system customers and suppliers. The reliability requirements are defined and accomplished based on the following 3 objectives. So 785, for those that don't know this document, was a book of 202, 301. And that would go into a contract and say, we're only doing these tasks of 785. But a lot of those tasks, you know, people don't use. And even though it was provided as a standard that people should follow, it allowed for tailoring. And a lot of people usually did that as they tailored out these tasks. So instead of having another cookbook with 30 or more tasks, we said these are the 3 tasks. They are determining the requirements of the customer, determining a process to satisfy those requirements, and assuring that the customer that the requirements are met. So pretty simple. Just tell me what you're going to do, write it down, develop a process, and then prove it. So how do you prove it? And that's what I was going to get into is next, is having design for reliability. So design for reliability is how you apply reliability engineering and reliability technology to ensure that we meet the reliability requirements, that we prove it and can demonstrate it. So the DFR process overview includes assessments, predictions, prevention of failures. Prevention is first. That's what we do when we assess a design and we determine that a failure is possible. So we try to eliminate that failure. So we prevent that failure from occurring. And if we can't prevent it, then we try to predict it and say, how often do we think it's going to occur? And if it occurs, how bad is the effects? What's the severity of the effect of that failure? So DFR, designing for reliability, aims to design for zero failures of mission critical system functions. So if a mission has a critical system performance parameter that must be met for that system to satisfy its requirements, then we don't want any failures of that function. So in designing for reliability, we try to eliminate that possibility. But if we can't eliminate it, then maybe we prevent it or minimize it, minimize the risks of it occurring, but it still could happen. But maybe it's not something that'll happen in my lifetime or my kid's lifetime or my grandkids' lifetime, but it will happen over a period of time if that system stays out in service for a long period of time. So depending on how the customer feels about those, if it's a safety critical, not just mission critical, or cyber critical, security critical function, then maybe there's enough of a catastrophic effect that nobody wants that to happen. And no matter how remote the chances are, we don't want it to ever happen. So let's eliminate that possibility. So DFR is involved in that decision. And also, there's also the results from the cost savings. So if we know that this is a failure that's going to cause a lot of maintenance and it's going to cost a lot to sustain or support the item in the field in applications where customers are expecting perfect performance and they have nuisance failures and they keep sending it back to the supplier to get it fixed, well, that cost could also drive these decisions as well. So I like to talk about the two P's. I mentioned prevention and prediction. So a lot of people in reliability, they get into being a prediction expert. But I like to say that you should start off as a prevention expert. And the way you become a prevention expert is by learning all you can about the functions of a system or product. So you have to be equal knowledge to the designer that developed the product, but then you're going to have more knowledge than the designer because you're going to learn not only how it works, but how it fails. So usually the designers, they design something so that it works once, twice, maybe 10 times. And after it works enough for them to be satisfied, they hand it off to somebody else and they'll say, you know, mass produce it, make it design for manufacturability and for repeating testing, let's say for repetitive testing in, say, a production environment or a customer environment. So those designers don't like to get into that area, so they hand it off to different people. And being a person with the knowledge of the design that can use the system, usually you're going to come across problems in the system that the designer didn't think about. And you got to go back to the designer to ask them what happened here. How come this is failing? What were you thinking when you designed this particular function in a certain way? And if the person doesn't have a good answer, then you should be able to suggest an alternative measure that you think will, like I said, eliminate a failure cause or eliminate a failure mode or eliminate the failure effect and greatly increase the time to failure if that failure mode or failure cause can't be eliminated. So you increase the time to failure. And that TTF is a parameter that is tracked statistically, and that's what we make predictions on. Like one of the parameters that we'll predict besides just the reliability probability is a mean time to failure. And a mean time to failure is usually for a non-repairable system or a non-repairable product, like say a light bulb. You'll have a mean time to failure, which is mean time to first failure. But if it's an item that's repairable, then instead of it being an MTTF, it would be a mean time between failures, so MTBF, where that item, that product, could be sent back to the manufacturer, have a component replaced, and then send that product back so that you can have multiple failures over its lifetime for that same serial number of product. So that's the kind of metrics that would be tracked. And a lot of times we'll do that statistical analysis and we'll measure the time to failures, put it into a tool like Minitab, or there's various tools out there, Weibull++, and then you have it calculate the reliability or the MTTFs or MTBFs, the failure rates, or the failure intensity or hazard functions. There's various parameters associated with reliability metrics. So that's what you're trying to do, is to prevent those failure mechanisms, and you use various tools like redundancies, M out of N systems, like I need 5 out of 10 systems to work for the system to work, or I need 2 out of 3 to work for the system to work, which means I could have 1 out of 3 fail and I could still accomplish my mission. Fault tolerant architecture, which is a system that can tolerate multiple failures like redundancy, but there's other ways to tolerate failures like error detection, error correction features through software. So those are just to name a few of the mechanisms that are in place for DFR to prevent failures. And by the way, when I worked at Raytheon, I worked on a program with South Korea, and I'll tell you, the South Koreans were really interested in this DFR, and they had paid Raytheon a lot of money to have me teach them DFR. And I would say it's about a 3 or 4 week, if I remember, training class where I had like 8 students from South Korea learn all there is that I could explain about DFR. But what I do here is to explain what I consider the top 3 things that you'll see. And I mentioned failure modes effects, and I'll get into a little bit more detail on a type of analysis that analyzes the failure causes, failure modes, and failure effects. So then going into the predictions where I talk about those metrics, if I can't get rid of the failure, I can't minimize its effects, then I have to predict it. And so that's when we use the time to failures, time between failures, and make those predictions to decide what the risks are. How critical are the risks of these effects due to failure occurrence, the probability of an occurrence over time, and then the severity of the effects of that failure. So prediction methods include fault prediction models. There's handbook approaches, like a very famous handbook, that Mill Handbook 217, has been out for many, many years, going back to the 70s, maybe even earlier. And that's been canceled. And there's standards out there that are like it, but nothing that quite duplicates that handbook approach, where multiple failure rates for different devices are added into the methodology for calculating failure rates of a system, where you add up the failure rates of all the components in that system. Then there's also empirical data that can be accumulated from testing or from field applications, where the customer is monitoring failures in the field and provides that data to the supplier to be able to do those predictions. And then there's predictive analytics using artificial intelligence and machine learning, data-driven methods, and Bayesian approaches that can be used. And by the way, a lot of these methods are explained in IEEE standard 1413 and 1413.1, if anyone's interested to do a deep dive into these methods. So then in the DFR process, there are 8 paradigms. And by the way, this is a reference to a book that I wrote with Raheja back in 2012. So I extracted these paradigms from that book. So the first one is to learn to be lean instead of mean. It's kind of a play on words. If you're familiar with lean manufacturing, where you do it right the first time and you try to be as lean as possible to only have the processes in place that warrant the most value in getting the product tested and out the door perfect to the customer. And instead of being mean, it's like being lean and mean. Like a fighting machine is kind of a term that's used a lot. You don't want to be mean, but you do want to be lean. And then there's also a play on the mean distributions, right? Mean time to failure, mean time between failures. So the idea is to be lean, which is to prevent the problem and not worry so much about the mean. So that's kind of pointing back to my previous slide with the 2 Ps, with the first priority being preventive. The second paradigm is spend a lot of time on requirements analysis. You notice how 1332 is written, all about the requirements. So that's what we said in the book as well, making sure you spend most of your time when you're doing your reliability projections of how much money and time it's going to take to do reliability work, is spend a lot of the time on your writing of the requirements, you're analyzing the requirements, you're verifying those requirements. So everything should be pointing to requirements in one way or the other. Measuring reliability by life cycle costs. So reliability is a direct relationship to costing. If I spend a lot of money in reliability, there should be a return on investment, which means if I didn't do the reliability technology added to a design, then there could be a large cost. So I used to say ROI of 10 or more. Or we also look at it with paradigm 4, which is designing for twice the life. So you can look at it as designing with a lot of margin so that you're not just trying to meet what the life of the system is, which might be, say, for a cell phone, might be 2 years. So if it's going to last for 2 years based on customer requirements, you want to design it to last 4 years. And then paradigm 5 is saying that for safety critical components, you want to design it 4 times the life. So instead of it being 2 years or 4 years, you want it to be 8 years. And so that's a ROI that's involved in safety critical as well when you get sued. So if something causes a fire and people die, what comes to mind is airplanes. I used to work at Honeywell when I knew Rajesh, and I worked on flight decks. I worked on safety critical systems for Boeing and Airbus, large carriers, large revenue generating airplanes. And that was a big consideration on how much margin do I have, and not designing for the minimum margin, but for as much margin as we think is necessary to ensure that people will be safe. Sixth paradigm is learning to alter the paradox of cost and performance into win-win situations. So it's kind of like teaming with designers. If a designer wants to test it once and prove it works and move on to the next design, try to hold that designer back to get their interest in it lasting longer than once or 10 times, but trying to show statistically how we could demonstrate the reliability maybe after 100 tests. And when I say 100 tests, I'm not talking about something that has to be tested for weeks or months, maybe a day or a couple of days running, very fast repetitive testing on a certain type of design just to prove that that design, which had a low reliability in the past, could now have a better reliability with an improved design. So that's kind of a win-win, is turning a designer into somebody that cares about reliability and then, learns from that experience so that they will do it better the next time they design a system from scratch. And then number 7 is designing to avoid latent manufacturing flaws. When I worked at Honeywell, again, this is where I learned this, is that we didn't just do reliability in the designs, designing for reliability. We also did it in manufacturing. And when Honeywell worked with Boeing, they had a process called RIM, which is reliability in manufacturing. So not only did Boeing and Honeywell want to prevent failures during the design or qualification process of a new product, but they also wanted to make sure that that design for reliability was flowed into the manufacturing process with a lot of lots of parts being shipped out, like on a monthly basis or whatever the time scale is for shipping lots out, weekly, monthly, or whatever, that there was a sample that would be pulled and do reliability testing in manufacturing. And then that's done through various means. And I'll talk a little bit about that coming up. And then the last one is designing for prognostics and health monitoring. To me, that's the future for predictions, is that we design for prognostics and health monitoring so that the system, let's say an autonomous system, is aware of its health and can warn a user or an operator or a design authority that it's got a problem that's about to go wrong. So don't wait until a catastrophic condition occurs, take it into maintenance and have that problem fixed as a preventative maintenance as opposed to a corrective maintenance where the failure has now occurred and something bad is happening. So the 3 DFR techniques I mentioned earlier that I consider the best techniques to ensure high return on investment when you offer a change in design to improve reliability starts with HALT. So I'll talk about that in the next slide, but highly accelerated life testing or highly accelerated stress testing. They're kind of used interchangeable, and I'll explain that in the next slide. You see, I said highly accelerated stress testing, and and you can also put L in there, and you'll see in the next slide how I tried to demonstrate that a little bit better than throwing people off by not putting HAST. Mostly people understand HALT in the system world or the product world, but at the supplier world, like for devices, integrated circuits, small components and devices, they're called HAST. So they're kind of used interchangeably. But then also explain the difference between HALT and ALT, which is accelerated life testing, which is not highly accelerated. The next one that's I consider very important to do in the design process to design for reliable systems is electrical stress analysis, followed by derating guidelines. I'll explain what that means. And then last is failure modes, effects, and criticality analysis. So the FMECA is a process that's used very pervasively throughout industry. And I'll explain that. So HALT, the basic idea of a HALT is that you have various step stress conditions and load cases. So the difference between an ALT versus an HALT is HALT has these changing steps conditions, like you start off with a temperature, say a high temperature of, let's say 85 degrees Fahrenheit, then you step it up to 95, then you step it up again to 105. So those are considered step stress conditions. And then load cases are where I do a load case of, say, high temperature step stress. Then I do another load case of low temperature step stress, stepping down. Then I do one where I'm doing vibration, let's say random vibration or swept sine vibration. So I'm doing vibration and stepping it up in the vibration levels or the G levels or G squared per hertz levels. And then I could also do combined environments. So HALT allows for combined, let's say, temperature and humidity or temperature and vibration, all going through step stress conditions. So as you can imagine, that's accelerating time a lot faster than if I was to do a steady state condition and not stepping up the stresses. So there's acceleration factors related to every one of those steps. And depending on how much time I run at that condition, the acceleration factor could be, let's say, 2-to-1, or it could be 10-to-1, or it could be really extreme, like 1,000-to-1. So 1 hour in test is equivalent to, say, 1,000 hours out in the field, under the customer use conditions. So another big difference between ALT and HLT is we like to say ALT, you can use that to calculate reliability. So the time to failure data coming out of an ALT would be used with Weibull, let's say, to calculate the distribution of failures. So I could plot a cumulative distribution function or a probability distribution function with ALT, where HALT, we warn not to do that. Some people are playing around with that, and I've seen some papers recently that point to that possibility of taking HALT data and using it for making predictions and proposing a reliability number. So that's possible, but in my past, when I did a lot of HALT testing, I didn't advocate using that data to calculate any reliability for the future. So you might say, well, then what's the purpose of it? Well, that's going back to determining design margin, which is my last bullet there. I could still determine what's the margin in my design. So if I know I run at these extreme conditions and I have a failure, then I question, is this failure something that could be experienced in the field? I just accelerated this failure mode, and now I find this problem. Should I fix this, or is this a one-up random isolated condition that I don't need to worry about and I don't need to fix it? So that's what you really get from an HALT, is finding problems faster and then deciding, do I want to fix it and add more margin in my design, or do I want to leave it there and then maybe worry about predicting it later? And then I said I was going to explain the difference between HALT and HAST. So in HAST, there's a lot of different meanings to this. And I kind of touched on that earlier, where depending on where you are as a system level, we consider that a HALT as a life test versus a HAST for components. But also, it looks at the fundamental limits of the technology. Both of them are concerned about those fundamental limits. But an HAST already knows what those limits are. They think they know what they are, and they're going to demonstrate them. So let's say I want to take a product that has plastic encapsulation, and I know that that plastic will melt at, say, 150 degrees Fahrenheit. So I don't take the testing up to 150 where I know it's going to melt. An HALT would be something where I take it to the destruct limits because I don't know where it's going to fail. So I don't have a preconceived notion of what those fundamental limits of the technology are. So then I'll say HALT, I'm going to determine what those limits are, where HAST, I already know what they are, and I'm going to keep under those limits. So hopefully that makes sense to give you awareness of what those two meanings are. And then HALT also has another advantage over an ALT in that an HALT usually leads to a HAS, so a highly accelerated stress screen, which would be used in manufacturing instead of an ESS, which is an environmental stress screen. So usually an ESS, the environmental stress screens, like say temperature cycling for weeding out infant mortality or workmanship conditions, manufacturing defects, making sure that you don't have any defects in the build operation that gets shipped to the customer. We call those test escapes. So I want to make sure that I don't just test it, say at room temperature, but I stress it at certain levels that are within the specs, right? HALT goes beyond the spec limits. It goes into what we call operating limits or destruct limits. But HAS does not take it to destruct limits, but from the HALT, we can then tailor a HAS using the same kinds of step stress conditions, but just not take it into the destruct limit, just work it underneath the destruct limit and within the operating margins, and then test it at that level in the manufacturing operation for, say, 100% of the product that gets shipped, or you pull samples and do it on a sampling basis. And HAS would be, in my mind, a better test than doing ESS. Okay, next slide is ESA and derating. So electrical stress analysis is basically calculating for any electrical parameter in an electronic circuit, let's say a circuit card or a printed wiring assembly. You look at the value of the, let's say, input current, input voltages, power. You look at what is applied versus what is rated. So the ratio of applied value versus rated value is that stress level, stress percentage. And then you compare that stress percentage to a derated value percentage. And then you say whether you're within the derating guidelines or you're at the derating guidelines or you're exceeding the derating guidelines. And then what would really be bad is if you're overstressed. And usually we like to say overstressed means you're exceeding the manufacturer's rating, but sometimes some companies I've worked for said if you're exceeding the derating guidelines, which might be, let's say, 80% of the maximum rating. So let's say the part is rated for 10 watts and I derate it to 8 watts. So if I go over 8 watts, some company will say, oh, that's overstress because you're adding some margin into that rated value. And then if you overstress it, the manufacturer will say, well, you send these parts back to me and they weren't overstressed. They're still operating. They say, yeah, but we're worried about it limiting its life. So you're taking away the reliability of that part by going over the stress levels. But there's multiple ways to derate requirements compared to stress values. And so when you look at overstress or right stressing, under stressing conditions, there's many ways of comparing your stress values to a derated table. There's various requirements that are out there. IEEE 2818 is IEEE's first standard that we're getting ready to publish that I talked about earlier, and that will talk about this whole topic of ESA and derating. We're also working with VITA, which is a VME standard that has reliability standards as well as like IEEE. They're a standards development organization, just like IEEE is. So VITA and what they call the VSO, which is the VITA VITA Standards Organization. We have a joint agreement with them to co-develop this standard 2818. So we're looking forward to that coming out very shortly here. So next one is the FMICA, and that's pretty much the last slide. I'll talk about, there's different types of FMICAs, and the one I'm going to talk about here is design function failure modes FMICA, considering hardware and software. There are such things, we call it D-FMICA for design FMICA. There's also P-FMICAs, which stands for process. So if you're doing a FMICA in the manufacturing operation, we call those process FMICAs. But if you're doing it in the design of a system or product, a D-FMICA, and we also call those functional FMICAs, or they could be a hardware FMICA or a software FMICA. But the one I'm going to talk about here is strictly a function FMICA, where the function is accomplished through the use of hardware and software combined. Now, I could have a function that's strictly hardware, or a function strictly software, or a function that's a combination of both. but the idea is that I develop a product or system that uses hardware and software to be able to implement a function or functions. So I want to talk about the difference between a FMEA and an FMECA. So a failure mode's effects analysis and a failure mode's effects and criticality analysis. Typically, the definition, you'll notice there's no C in the FMEA. So the C stands for criticality, and that definition points to a criticality analysis that was explained originally in a Mill Standard 1629, which is still available out there, even though I think it was canceled, just like Mill Handbook 217 was canceled. The FMEA typically does not have a parameter or a quantitative measurement for the risks of a failure mode, where the FMECA does. So for every failure mode and every failure cause and failure effect that you assess, you have a criticality number associated with that failure mode. In the FMEA, you don't. And the reason is because the FMEA is really looking to eliminate or avoid single point failures. So it's an assessment, again, to prevent failures, not necessarily to calculate and predict failures. So with the FMEA, I want to look for single point failures. And if I say, hey, if this particular, let's say, capacitor fails short in a circuit, and that shorts, let's say, a plus voltage, say a DC power supply or a DC battery to ground, then that means that we're going to have a short or a catastrophic condition like an explosion. If it's a large power supply, or if it's a battery, it's going to drain that battery really quick. So something simple as a capacitor, which could be, you know, like $1 or maybe even less than $1 for surface mount technology components, that capacitor fails short, and now you've got a single point failure that takes out that whole product. So we would look at those and assess them in a FMEA and give those a high or not a high probability, but a high priority to be fixed. And so what a lot of people have done, knowing that the difference between a criticality analysis and a FMECA versus a FMEA, where you're looking at priorities of failures that should be fixed, people have come up with what's called a risk priority number. So I've seen books that have been written where a FMEA generates a number, a risk priority number, and it's calculating criticality without going into all the details of a criticality analysis that's explained in a FMECA. So you can have a FMEA that's strictly without numbers, just to find single point failures, or you can have a FMEA that generates an RPN for every failure mode, and that's usually based on kind of a weighting, let's say from 1 to 10, where 10 is bad. So a high severity catastrophic condition is a severity 10, and that the higher the risk is the higher probability, or the higher need to fix that failure mode. So we have a 10-to-1 on the severity, 10-to-1 on the probability of occurrence of that failure mode, and then 10-to-1 on the non-detectability probability of that failure mode being detected. So let's say if I have a high severity failure mode, which can cause, let's say, a fire and cause harm to people, and I have a probability of occurrence that is very probable to happen, let's say, within a year of its use in the field, so that now I've got a probability of people getting hurt or killed, and now there's a liability associated with that, where I have potential of going to court and having large lawsuits against me. Then the next thing is, can I detect it? Is this something that I can find out it's getting ready to go on? It's getting ready to have a failure before it occurs. And so if I have a 10 on severity, a 10 on probability of occurrence, and a 10 on non-detectability, you could say, oh, okay, I multiply those 10s together and I have 1,000. So 1,000, anywhere a number between 1,000 and a 1 is one way to assess a risk priority number. And I've used those numbers in the past, and I've had numbers that I've thrown out before that companies that I've came up with this solution considered it proprietary, so I can't tell you, but you can imagine some number between, let's say, 200 and 300 or 200 and 400 would be a priority number that says, hey, within this range of numbers, I should be fixing anything that's worse than that. Like if I have a 400 up to 1,000, anything in that scale should be fixed. And anything below that, maybe within 200 to 400, I monitor it and see if it gets worse, see if it becomes a higher risk, and bumps it up maybe above the 400 range. And then if it's less than 200, let's say it's something that just a routine thing that I wouldn't have to fix and wait and see if anything more occurs like it in testing. And I think that's it. Just the last thing is just to show you the reference that I cite for the DFR stuff from the book that was published in 2012. So with that, I'll take questions.
Thanks, Lou. We have few questions. Let's start with this one. How does, like, when we talk about reliability, does it fit the quality control engineering? What are the quality and the quantitative aspects of reliability?
Yeah, the qualitative is when you do a FMEA, where you're looking at the level of failures that have single point failures. So failures that if they failed, the mission will not be accomplished. That's kind of qualitative. And quantitative is where I have criticality numbers that says, I'm monitoring the probability of occurrence, let's say in failures per million hours, or time between failures is getting less and less, like 8 hours between a failure, right, versus 8 years. So that would be one way to quantify the reliability and put weight on a failure mode being fixed to make sure it never happens again. So that's one way of looking at it. Severity is another way, how severe. Like in the safety community, system safety, there's a MIL standard called 882 that I've used a lot in the past. By the way, I also wrote a book. My second book was Designed for Safety, and I cite 882 quite a bit in that book. And that's another way to quantify the risks that have safety critical implications.
Thanks, Lou. Another question is, what's the difference between reliability and maintainability?
Yeah, I look at reliability and maintainability as like a teeter-totter. They're inversely proportional. So if my reliability is perfect, let's say reliability can be assessed as a number between 0 and 1. If my reliability is 1, that means it never fails. So maintainability is 0. I don't need to maintain something that never fails. So as the reliability starts to come down, maintenance now becomes a higher priority, and something that I was maintaining before manually, now maybe I need to automate that process. I need to put more software to detect indicators of a failure mode getting ready to happen. That's kind of what we do in prognostics, is predicting through condition-based maintenance approaches, health monitoring statusing, indicators of weaknesses or deviation in variables that say, hey, I have an anomaly that's happening, that's causing change in my control limits of a certain variable that I didn't see those changes before. They were very nominal. They were very minor fluctuations in that parameter, but now I'm starting to see large fluctuations in that parameter. Maybe it's still within the spec limits. Upper and lower spec limits are still being met. If I went over the spec limits, that's a failure. But if I went over, say, a control limit, where I'm monitoring and controlling that parameter, and it went over the control limits but under the spec limits, that's an indicator of something getting ready to fail. So I better take a look at that to predict the failure and possibly stop it from happening before it occurs.
Lou, just extending that, you want to talk a bit about availability, because both reliability and maintainability.
Yeah.
Thanks.
Yeah, we consider availability as a combination of both reliability and maintainability. So the equation that I like to use for what's called inherent, there's different types of availability. There's operational availability, inherent availability, so material availability. So I like to use the term A sub I. So A sub I is inherent availability, and the equation I use is MTBF divided by MTBF plus MTTR, where MTBF is mean time between failures and MTTR is mean time to repair. And so those two parameters, one's reliability based, one's maintainability, are used to calculate availability. Now, another thing is availability is more applicable for certain types of systems that are operating like a telecom system that's operating 24/7. So if a system is constantly operating, availability is looking at the probability that given the system is operating and is supposed to be operating all the time, what's the probability that I want to use it? Let's say I'm not using it up to a certain time, but at a certain time I'm going to use it. that it is not failing or it's not in maintenance. So what's the probability that it's up when I need it to be up? As opposed to reliability is, given that the system is not working right now, and I turn on a light switch, let's say, or I initiate a button to initiate a function, what's the probability that it will work over that period of time when I need it to work, and then it can stop working? Or it's like a one shot. You know, I shoot the missile and it lasts for, say, a few hours, and then it's not needed anymore because it's done its job. So that's kind of like the difference. Reliability is like a certain time dependency from it not being operating to operating, where the other one is availability is operating all continuously, but now I'm going to need to operate at one part of that timeline.
Thanks, Luke. Probably this will be the last question, unless I know we have already run out of time. I'll just ask this last question. If you can keep it short, please. What are some of the challenges of ensuring reliability in modern manufacturing?
The biggest challenge is probably getting testing approved to do reliability testing in manufacturing. Like when I worked at Honeywell, I had to convince management to buy a lot of halt chambers, which at that time they were about $100,000 a piece. And I said that we would demonstrate a lot of reliability that would go a long way to reflecting that reliability to our customer, Boeing and Airbus, and then being also used by those two airframe manufacturers to their customers, like American Airlines or Cathay Pacific, you know, JAL, ANA, Lufthansa. So everybody that uses a Boeing or Airbus airplane would want to be able to advertise a reliability number that would come from me. And so I wanted to provide that empirical data to substantiate a reliability number for a piece of hardware that we were delivering to all these airplanes to support what we're saying. We're not just giving an advertisement that our reliability is, say, 0.99 or 99%, but the reliability is based on this amount of samples collected over this amount of time with this amount of failures.
Thank you, Lou. I think we are out of time, and there are several other questions on the chat as well.
We can run a little bit long. I said,
sure, I'm good.
Yeah, as long as our speaker is good.
Yep.
Okay,
good.
Lou, you're okay?
Yeah.
Okay. A few other questions we have is, what are the different types of reliability testing? I know you covered a few.
Yep, there's a lot of, I talk about it in the book, but there's a mill standard or mill handbook 781 that's also been canceled that somebody could take a look at, that has all the different flavors of reliability testing. Some of them are called hypothesis testing or reliability demonstration testing, reliability qualification testing. There's one called a PRAT, which is a production reliability acceptance test. They have them either as a sample or they have what's called an AE PRAT, which is an all equipment production reliability acceptance test. There's also PRSTs, which is probability ratio sequential tests. So these are all different test plans and test methods to use in manufacturing to be able to demonstrate reliability of a lot that you're shipping as you go through your manufacturing processes.
Thanks, Lou. You want to
mention? I want to mention another book that I remember reading that I really liked. It was by Wayne Nelson, and it was on accelerated stress testing, ASTs. I really liked his book, and he does a really good job of explaining how to do like using models. Like I talked about reliability models for predictions. There's one model that's very well known called the Arrhenius equation, and it's basically a way to use temperature to come up with an acceleration factor for your testing that could be used to demonstrate reliability in test that can be equated to the field. So that Wayne Nelson book is very good too.
Thanks, Lou. You want to talk a bit more about the FEMA FMEA from reliability perspectives?
Yeah, I talk about that in detail in the book. There's also a book that Anne-Marie Neufelder wrote on effective software FMECAs, which I like a lot, and I reference that a lot in my work that I was doing before I retired. There's also Carl Carlson. He used to work for GM on automotive, and he wrote a really good book on Famicas. So I would say there's a lot to it. There's many ways of doing a Famica. There's no one right way. I mean, 1629, mill standard 1629 is the way I was taught, and I could do it. I was doing it, 2 or 3 years ago, and it's still being used today. But there's a lot of other methods out there that could be considered. So there's no one right way to do a Famica, but I think the bottom line is you want to find those single point failures to prevent failure modes from occurring.
Just an extension of it, FTAs. You want to touch on that? The failure
Fault tree analysis. Yeah. A lot of people like to use fault trees. I have used fault trees before, not as much as a Famica. So Famicas can be a top-down method or a bottom-up method. Like when I say bottom-up, I'm saying I look at the components on a circuit card, and then I look at the failure modes of the circuit card into a box, and then the box failure modes into a subsystem, and the subsystem failure modes into an overall system, and maybe a system into a system of systems. So that's usually a bottom-up approach that you can use Famica for, but you can also do a Famica top-down, which is what we do with a functional Famica, where we look at all the causes of a system failure, and then the causes are at the next lower level, and then we say a failure effect at one level is a failure cause at another level, and we work our way down. Well, a fault tree analysis does that more top-down analysis, but then it puts it into a diagram that you can see how these different failure modes work combinational logic, with an and or an or gate, how they apply in causing a top level system failure. So you might have redundancies, parallel systems running in tandem that you can have one as a spare for the other one, having two channels that are doing the same job. So maybe they're both sharing 50% of the load, but if one goes down, then the other one takes 100% of the load, and you could still get the job done. So you're considering all of that when you're looking at a fault tree analysis. Also in a reliability block diagram, RBDs, I've seen where you have tools today, like Reliasoft does this, where they have a reliability block diagram, and you show the serial parallel configurations of your functions, and then from there you can develop a fault tree automatically. So they're kind of intertwined. You put the logic into one model, and that could be used in another application like a fault tree.
You touched a bit on system of systems, the SOSI there. You want to talk a bit more about how FTAs or FEMAs can be applied to complex systems?
Yeah. I say at a functional level, at the top down, looking at all the causes of a system failure based on, let's say, their features or their requirements, looking at how many shall statements are in a requirements document. If it's a defense, usually there's a spec, specification, like a design spec that's agreed to by the supplier and the customer. Or if you don't have a spec, let's say you're a company like Ford or a car manufacturer that's selling it to the general public, so you don't have a spec, you might have a marketing requirements document. So one way or another, you're going to have some document that defines your requirements for what this design needs to do. And then you're going to analyze those requirements and look at the system as a top level function, set of functions, and then everything below it could be black boxes. By the way, getting into the analysis of each of these boxes that perform functions for a top level system, you could do what's called a black box, where I'm only concerned about the inputs and outputs, but I don't know how the box performs. Or there's white box or clear box. There's many ways of assessing a box and going down into the lower levels. Like if you're buying a product that's off the shelf and it's a standard product, like you could buy it off of a catalog, the supplier of that part is not going to want you to ask and share with you its parts list or its schematics, or its assembly drawings, right? That's like giving away the secret sauce of how they make their parts or proprietary information. But on other cases, like a defense contract, that's part of the requirements, that you have to share all that design. So whether you do a black box or white box, let's say, or clear box, how you understand how that design works needs to be part of your methodology and your reliability engineering processes of how you're going to deal with all these lower levels in the indenture tree of that design, from, say, component level all the way up to the system level, and assessing, like a FAMICA, how far down do I go? Do I go down to what we call LRU, which is a line replaceable unit? Usually that's a box. So if I say, hey, and when I'm on the field, all I'm repairing or replacing are boxes. I'm just switching out boxes. I'm just disconnecting a cable, replacing that box with another box, recabling it up, and then turning power on and retesting the system. So it all depends on your maintenance concept, and it depends on what you've got reliability requirements for. Sorry, my cat just jumped on the lap here. Does that make sense?
Yeah, it does, Lou. So that actually asks a few questions related to systems. We have been talking about systems, but systems contain not only hardware, but also software and resources like data. So how does reliability apply, say, to software and data? Maybe we don't have to cover data now. It can become very long. Maybe just touch on software part.
Okay, yeah, software is a different entity than hardware in how you assess it from a functional viewpoint. Since you're not really replacing software, you're just recoding software, and maybe you're replacing a file. But a lot of times, if it's in design, you're just replacing. Sorry, not replacing, but just maybe editing a file, creating a new file name, and then reloading that into your microprocessor. So software is, it's got a lot of connotations with intermittencies. It's hard to duplicate. There's a lot of probabilistic mechanisms as well as deterministic mechanisms in software. But the same could be true with hardware. But the thing about hardware is hardware ultimately will fail, where software doesn't necessarily have to fail. There's a possibility that software could be perfect. If you're developing synchronous code, it's a state machine. I mean, you run through all the truth tables, the number of inputs and outputs. You test all those inputs and outputs, all those test cases, use cases. If you test it enough, you could say that I think the probability is 1 for that software. You can demonstrate that and prove that. So reliability for software is possible to be a 1, where I would not say that for hardware. Hardware, I know ultimately it's going to fail. It's not if it will fail, it's when will it fail, because it wears out.
So I guess it's a question of like looking at a perspective of how in a software, we don't have to replace the hardware, but given the limitations of the hardware, we can enable it to be programmed so we can utilize the resources in the hardware to reduce the mean time to failures.
Yes. Yeah, that's stressing it less. So you can alter the hardware failure rates by stressing it less. Yeah. And software, that's possible as well. Like for interrupts, how many times do I have an interrupt and go into an exception handling? There's that way where you break into the code. If I'm running a synchronous routine and then I have an interrupt, do I know that I can go back to a last known good checkpoint? Is there a way to track where I was in the software when the interrupt broke in, so I can come back to it and then continue processing? Or am I lost? Do I have to start back at 0 again, or start at the first instruction?
Yeah, you bring certain points that bring up discussions about how the semaphores and the mutexes and the way interrupt handling works, and in a way can cause other security issues like buffer overflows, for example.
Yeah.
I guess that would become very long discussions. I guess interested people can contact you after the session.
Yeah. Yeah, let me just say that for software, I've assessed a lot of software failure modes. And I think like when you talk about buffer overflows, stack overflows, to me, that's part of a memory leak condition. And I know there's various ways of looking at, memory and overflows. But I consider the way you map the memory, how you do memory allocations, how you manage memory, like an MMU, memory management unit, like a lot of the software that you can buy for real-time operating systems come with a board support package that contains a memory management unit. So how you use that memory management unit can mitigate a lot of risks related to memory leaks. So usually when I see memory leaks happening pervasively, that's because they're not using the capability that they have in their BSP, using an MMU properly.
Lou, unfortunately, we need to stop here as we are almost 15 minutes above the time limits.
Mm-hmm.
Thank you very much, Lou, and thank you all for participating.
Will you be sharing the slides with everyone? It's okay
yeah.
for me.
Michael?
Great. Yeah, so typically the recording of this session will go up to YouTube possibly as early as next week. But certainly sometime in the next few. We've kind of had our hands full on coordinating things through the weekly sessions over the last week or so. So if you're attending this session, just bear with us, and we will get the video up just as quickly as we possibly can. The next session is on July 23rd at 7 p.m. And I believe, Rajesh, that's one of the sessions that arranged.
Yeah, that's going to be Arun Vishwanathan from NASA JPL. He'll be talking about his experiences in space and the securing of space.
Who's that?
Arun Vishwanathan.
Arun? I've heard of him.
Yep.
Okay.
We are working together for some of the space security standards, Lou.
Great. Yeah, before I joined Northrop Grumman, I worked for JPL.
Mm-hmm.
All right. Well, thank you everyone for attending. Thank you to our speaker for agreeing to speak to us tonight.
Of course.
We hope to see you guys again next week on July 23rd. Have a good night, everyone.
Good night.
Thank you all.
Bye-bye.
Bye.